We're starting polynomials, one of the families of functions. Do you remember what polynomial graphs look like? So if I were to graph a quadratic, what's that called? I think John already said it. Right? Okay. We're not going to get that deep, no. We're going to get somewhere with it. Okay, so we have quadratics. That's going to be our biggest focus the next few weeks.
Are we doing like
you know the cubics, right? Okay, they can look as such. And I'm going to put axes here. We're going to come back to this here in a bit. Okay. Yeah, that's a weird one. I drew it like that on purpose.
oh crap, I drew it in 5 places. I don't know how to draw it. I don't know how to draw it.
Okay, I'm missing one. Can anybody tell me what it is? Or, well, I'm missing about an infinite amount, but.
Wait.
Anybody?
For quadratic, you have to touch it in the x-axis in 4 places, or
Up to 4.
the x-axis?
Up to 4 times. It doesn't have to be 4. It can be 0.
And it's still a quadratic?
Yep. Well, we're going to actually explain that today.
Perfect.
Parabola, no, as a quadratic. I am missing the most favorite one of yours. Linear. I'm not going to go into the upper level ones. We're just going to let them be for now. Okay, what would the example equation of a quadratic be? I said equation. Y equals x squared. It has to have an equal sign if it's an equation. Yeah? How about a cubic? Quartic? And linear? Yeah, those are all the parent functions, right? Okay, those are all polynomials. I can keep going, x to the 5th, x to the 6th. How many polynomial functions are there? Yeah, an infinite amount. Okay, so we can have all sorts of fun for the rest of eternity with these, but we're not going to go that far. Okay. What is the degree of that function? Jesus, do you remember that vocab word? Degree? No. Degree of a quadratic, anybody? In here. I would do well to repeat what Chloe just said. Oh, you didn't hear her either. Okay. Degree 2. It's cubic degree is, okay, you get the idea? Because of the exponent. And this is degree 4 and linear degree 1. Okay. How many solutions? You guys remember what zeros and roots are, right? Okay, there's one interpretation. The value of the function is 0. I'll show you an example here in a minute. The graph has an x-intercept. Okay, that'll be the location. Oh, I didn't know it was that bad already. Are we in for another fun week with functions? Woo! Right. Okay. How many zeros or roots does that function have? Okay, there are 2 x-intercepts, right? How many are here? How many are here? Okay. How many can I have up to on a cubic? Yeah, I could do this, and there would be 3. Can I ever have 0? How? Oh, now we got to think. Say that, how?
It's like on forever. Oh, you could have a parabola one because it could be up above.
Okay, you're both right. Okay, I could be above the x-axis with a parabola, right? No solutions, no zeros. Or I could be 0 slope on a linear equation, right? The quartic can do that too. Okay, so what you're seeing an illustration of is the fundamental theorem of algebra. Okay. We can have up to 2, so the degree of a polynomial. Oh, we have another fun dimensional theorem. This is not word for word, okay? Not word for word. This is a summary. The degree of a function is the maximum number of complex roots, zeros of the function. Okay, we're going to use zeros and roots interchangeably. There is a difference between the 2 words, but we're going to use them interchangeably because it's really not that big a deal. You guys remember your number systems? Okay, why didn't I put that it's real solutions or zeros? That's the question. So your number systems, we'll see if this rings a bell. Remember these? Natural numbers. What's next? Which one is it? It's the whole numbers. The whole numbers add a 0. So they include the naturals. I'm explaining to you roots. What's next? The integers? Oh, thank you for the correction. Which tack on some negatives. Oh, I know it's bad. The rationals are next, right? I'll describe those as all fractions. Made with integers. Now, where are the irrationals? They're kind of outside here, huh? Because they don't make sense. Okay. Can you give me an example of an irrational number?
Pi.
I like pi. Had plenty of it this weekend. Something's wrong with you, honestly. What are all those together called? The real numbers. Okay. What was outside the real numbers? Yeah, what are those called? Close. Okay, so we have the imaginaries. Okay, now whoever said complex, what did both of those make up? That was yes.
Why is pi irrational? Because it says non-repeating, non-terminating decimals, but it doesn't.
No, it doesn't.
1.5.
We have had computers on a calculation of that particular number for years, and they have not found an end or a repeat yet.
Okay.
That's all we know. Could it be a rational number? Yeah, but we don't know that. Okay, these are all together called the complex numbers.
What's the bottom say?
Real and imaginary. That's the complex numbers. So now you can read it, I guess, huh? All right, so why did I put all that on my paper? I don't know either. Of course I do. Of course I do. Okay, the definition, or here, the fundamental theorem of algebra involves complex roots. Okay, so we have to know what complex numbers are. How many, this black cubic here, how many complex roots does it have? It's a cubic, so it has 3. But how many real number roots are there? Just 1, because that's all the times it hits the x-axis. So this has 1 real, okay, 2 imaginary, or a total of 3 complex roots. Okay, so we know the difference there. We have imaginary roots if we're not hitting the x-axis. Just, that's FYI, right? Are we good there? Okay. Oh, that's- Okay. What's the degree of that polynomial? It's a 3. It's the highest exponent, right? And here's a question you're going to run into. Is 4 a 0 of f of x?
No.
Plug it in, what? What's the y value of an x-intercept? 0, right? So if I plug this x into the function, what should I get? 0. All right, so if I plug that in, I get 0. It's a 0. Let's try it. John, do you actually know this, or are you just guessing really well?
This?
Yeah.
It's actually kind of stuck a lot much.
Nice. I did something right in this unit last year. Most of you just screwed up.
I also struggled really bad last year with this.
16 times 6. 96.
Hey. Negative 32 plus 4 of course.
Oh.
8 minus 0.
Right?
Thus,
Plus 4
Does that make it clear enough? What's the x-intercept then? Yeah, 4. On the graph, the x-intercept is 4. So we're try to make those connections. Zeros, roots, and x-intercepts. Easy enough? All right. So far it's been pretty straightforward. Oh, that's a good question. I forgot something. What is... Yeah, you need to know it, so it's good. Okay, the leading coefficient on this one is 1. Okay, it's the number in front of the variable with the highest exponent. So a lot has to do with that term right there, right? A lot has to do with it. Thanks for mentioning it.
Okay, we have a couple more examples. Okay, here's your next one. We're going to write a polynomial with the roots of 2, 4i, and negative 4i. Right? Okay, what degree is this going to be? How many roots are there? I have 2, 3, 4.
3.
Okay, it's 3 because there are 3 roots. Degree 3, right? Glad we get past that. Question is, how do I write an equation with those? You know, that's true, correct? Those are your x values, the x-intercepts. How can I make those equal to 0? Thank you, Anir. Now we have 3 different roots because they equal 0, right? So y equals x minus 2, x minus 4i, x plus 4i. That is your equation. Bam! Yeah, it's easier than you think. If you're a forward thinker, x minus 2, x minus 4i, x plus 4i. It's just the opposite of each of these, right? Easy enough? Sure or not sure? Okay. Here we go. Okay, this is why I put the warm-up on the board. Okay, you're going to have to factor. So what can I do first? Okay, we're going to take an a out. Shoot it in the head. What's next?
4 times 2, 4 negative 2.
What are your roots? 0 equals 0, right? Negative 4 plus 4, and 2 minus 2. Where are my x-intercepts? On the graph. Yep, 2, 0. So what does that look like? Yeah, we're just going to do something like that. Okay, we're just going to sketch it. Do you want to be more precise on the graph?
No.
Okay, all you have to do, if you're paranoid, what's the function evaluated at negative 2? We get negative 8 plus 8, 0, 16, right? So this point would have to be negative 2, 16. So it goes way up above where I have it. And then 1 plus. And this would be at negative 5. So it actually does a lot bigger swoop than I have it. Okay. Okay, I have one more I want to show you just for factoring purposes. Do you remember how to factor those ones the fast way? Yeah, there's a 0 in the middle if you want to do it the slow way. It's called the difference of squares. So if you have something of this nature like x squared minus 9, x plus 3, x minus 3. Okay, because it's 3 squared and x squared. What about m to the 4th minus 16? You get the idea? We went over that last year pretty heavy, so hopefully you're okay there. All right, any questions? I've talked way too much today. Yes, he is. Yep. Okay, I'm trying to minimize the new stuff. Make sure you do the reviews too. Those are muy importante. You have about 10 minutes. I suggest trying to tackle, oh, those are all easy. 11 or 13. Those would be, so 11, 13, 14. 14 is the hard one for the section, and 43. Start on number 11, please. Yep, I expect to be done before you leave. I know it's out of order, but you can handle this.